of water. When you breathe, the atmosphere dissolves into that water. When your blood flows near that water, it exchanges gases with that liquid. That's what breathing is. You breathe underwater just like a fish. You had gills when you were an embryo. They turned inside out and went inside your chest cavity when you were a little bit bigger than a pinhead. Graham? Now those lungs would pick up this exact same stuff that you have stuck on here, except for the fact that your body has filtration. Anybody know what a luti is?
Mucus and saliva.
Mucus, saliva, and what else?
Particulates.
Particulates, the stuff you didn't want in your lungs. I think we call it phlegm when it's mucus plus garbage. Now here comes a pretty picture for you. Your respiratory system is like a waterfall of mucus going down. As you breathe, that mucus picks up particulates like this. But as that mucus gets sort of gunked up and accumulates more stuff, there's this like conveyor belt of little hairs that brings that back up to the surface. So two different forces. Gravity pulling that mucus waterfall downward, and cilia, which are these little hairs scooping the nasty upward. When that reaches the top of your throat, usually you swallow it. Almost all of that is involuntarily swallowed. Some of it works its way all the way to the top of your nose where it drips in and dries and drips in and dries and drips in and dries until it piles up and you get boogers that you can throw at your sister. Or eat. Yeah, we'll eat that. Sometimes, if you have a whole lot of phlegm, like you have breathed a bunch of particulates that your body got rid of all at once, you might cough them up and spit them out. Or if your body's trying really hard to keep bacteria out of your respiratory system, like when you have a cold, you also spit them out. Please look at your indoor sample. You probably see some really, really small flecks of dust. That's pollen, dead skin cells. You might see little short, clear fibers. They're about 1/4 inch long. Those are little pieces of plastic and carpeting and clothing fiber. If those get all the way into your alveoli, the really, really small ones, the ones you cannot see with the naked eye, the really, really small stuff, if that gets all the way into your alveoli, it'll kind of get stuck there. Those little air sacs inside your lungs. So if those fine particulates get into your air sacs, then first of all, they prevent air exchange. They clog your lungs, so to speak. And second of all, they might diffuse other chemicals into your bloodstream. This is why particulates make air pollution more dangerous, because they park the pollutant right next to your bloodstream. Does that make sense to everybody? You and me, because we're healthy, most of the particulates we breathe in are trapped, just like the particulates in your petri dish. And then our respiratory filter, those cilia, will bring that back out and we either spit them out, we drive them in our nose, or we swallow them. but not smokers. Because people who inhale a lot of smoke, those cilia, they freeze. The conveyor belt stops. They still have a mucus waterfall. They still trap particulates, but there's nothing to bring them back out. So for a smoker, all that stuff just fills in your lungs. Those cilia are paralyzed by somewhere between 2 and 6 hours when you inhale smoke. So when you inhale smoke, you are stalling your air filter. I don't need any details, but how many of you have been around a smoker first thing in the morning? I've woken up in lots of weird places. I'm not judging. If you've ever been around a smoker first thing in the morning, as soon as they get vertical, they start coughing and they got to find the closest place to spit like a giant loogie. How many of you have experienced this in the presence of a smoker? The reason this happens is all day long, as they have cigarettes, they paralyze their cilia and the mucus just packs into their lungs. That's why smokers are always out of breath, because they're literally drowning. The technical definition of drowning and the technical definition of what happens to smokers is identical. They literally have fluid buildup in their lungs and they can't breathe. So the smoker spends all day surviving on minimal lung volume. They have high blood pressure. They get hardened arteries because their arteries have to fight back against all of this blood pressure because they're moving the water really, really fast. Sorry, they're moving the blood really, really fast because it doesn't have enough oxygen in it for their body to survive. So they got to move it quicker. And all day long, they're filtered, their dirty mucus is just packing into their lungs. Then overnight, their cilia wake up, ship all that mucus up to a pocket at the top of their throat, and as soon as that smoker goes vertical, that glob starts moving around and they got to get rid of it. The rest of us who don't smoke, we have a functional air filter. All of that mucus full of particulates is driven upward. Not the smoker. The smoker, all that stuff is preventing them from breathing oxygen. Smokers have heart attacks because they don't deliver enough oxygen to their heart tissue. They have strokes because they don't deliver enough oxygen to their brain. They develop respiratory diseases more often because particulates are not kept from their lungs, and that includes infective agents. And they are much more susceptible to air pollution because particulates will park air pollution inside their lungs and give them more opportunity for that pollutant to get into their bloodstream. Yeah?
Are the cilia frozen by particularly tobacco and a cigarette smoke? Or like
So you smoke weed, huh? Fine. Calling your parents. You guys saw that, right? Witnesses. Any smoke will paralyze cilia. Thank you very much. Good news for you, though. You would need a whole lot of smoke to paralyze your cilia. So technically in the U.S., most of the marijuana that people smoke is super concentrated. And so you don't end up taking that much smoke into your lungs before you put it down. Like a really, 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 really heavy pot smoker, like a total record-breaking pot smoker, usually doesn't inhale as much smoke as a very light cigarette smoker. So there may be other problems with really heavy marijuana use, but it's probably not the smoke issue. Yeah.
What about vaping?
So In that case, there may be other separate problems. Vaping has a really short medical history. There may be other particulates involved, depending on, like, if you're just vaporizing marijuana stuff. It's my understanding that that's relatively safer for your lungs. Chemically, getting stuff to that temperature might have other consequences that I'm not qualified to speak about, so I'm not saying it's safe. But at least it's not smoke inhalation in large volumes. Vaping, the way that people use to take nicotine, so separate from marijuana vaping, but like vaping like e-cigarettes, that may have a lot of other chemical ingredients that I don't know about. Whether it's for nicotine delivery or not, smoking anything that's been carried to that temperature is going to probably have a lot of volatile organic compounds, hydrocarbons. But the paralysis of the cilia specifically depends on smoke volume. So firefighters get that. People who cook over an open flame get it. And cigarette smokers get it. Are there any other marijuana questions? Guilty giggles, like half the class starts blushing if you just go like marijuana, marijuana, marijuana. Oh, they're blushing. Like everybody's like,
Where?
It's not me,
Where?
stop looking at me. You got no game face, kids. You got no game face. Lure? Okay. Okay. If you've looked at them already, I'm kind of good. There was a post lab, but I've decided to scrap that because it's really hard for everybody to do their results in the time that we have. I don't have enough dissecting microscopes. Problem. Okay.
What are these called?
Those are called loops. LOU. So now, students, now we need to talk about number 41 and 42. First of all, there are three categories of ultraviolet. Ultraviolet is the high energy extreme of the light spectrum. So there's low energy, light, and ultraviolet at the high energy. Ultraviolet gets divided into three categories, A, B, and C. Those are a measure of their wavelength. Look, if you've got to cover this much distance, please look up, in a single wave, that's not a lot of energy. But if you shorten that wavelength, it takes a lot of energy to cover the same distance. You guys notice how many times I had to move my arm, right? So this requires a whole lot more energy than this. Long wavelength is low energy. Short wavelength is high energy. Yeah.
So long meaning this is long, and short meaning, up and down.
The length of the wave.
Okay.
It's not the amplitude, it's how long it takes to go up and down, right? Now, to explain blockage, I have to use an analogy that is probably getting outdated. It's funny, you teach this year after year after year after year, and you see how the world is changing in ways you didn't think it would change. How many of you have either played a real actual pinball machine or seen someone play a real actual pinball machine with a glass top and a metal ball? Cool, okay, so we're still living in the past.
Yeah.
I'm hoping that you guys will remember this. It's hard to explain it otherwise. There's these little things called bumpers. They're round. And if the ball falls between them, nothing happens. But if the ball bounces off one of them, what happens? Okay. This is the best analogy I have for how wavelengths interact with chemical compounds. Remember, a compound has many elements, like H2O has 2 hydrogens and an oxygen. And please look up. Those elements are held together by a bond. Please look up. A long wavelength might go all the way through without actually bumping into those atoms. However, if that wavelength, please look up, can bump into 2 of the atoms, it separates them apart, can break their bonds, use up the ultraviolet energy and give off heat, like this. Please look up. This is ultraviolet B, bumping into ozone. Bumping into ozone, it'll break that bond, give off some heat, and make O2 plus a single oxygen. Yeah?
The heat is coming from the bond separation, not from the UV.
Yeah, so I mean, essentially you're adding the ultraviolet energy to the bond. With that much energy, the electron can't be shared anymore. One of them, I don't know, gets too excited or something, and so it'll separate from the compound. The electron will come back down to the appropriate energy level, and it's the leftover energy of the bond plus the ultraviolet boost. Okay.
So the UV will then break the bond,
Basically, yes.
and the bonds are in the stratosphere, right?
So those bonds are everywhere, and this is the part where people get a little bit confused. There are chemical compounds all the way from the center of the Earth to the surface of the Earth, throughout your body, and in the air above you, right? There's ozone and oxygen and O2 above you. There's all sorts of fats and proteins and I don't know what the hell else in your body. Now, some of these bonds are not close enough to to be broken by the low energy radiation. Best way to say this, please look up, is that a long wavelength can squeeze between without hitting the atoms. It's not very likely that ultraviolet A with its long wavelength will hit atoms in a bond. So that stuff is what we call penetrating energy. This can usually make it all the way through the atmosphere without bumping into anything. It can penetrate through many of your chemical bonds in your skin before it eventually bumps into something. And when it bumps into something, it could be all sorts of chemicals that don't matter, or it could be DNA, which is important for your skin cells. Yeah?
So when it finally bumps into something, then there's a reaction that occurs, but then does suddenly the wavelength stop? Or
Yeah,
is
it's
it just
energy, and that energy is used up.
It's absorbed. Okay.
Right. So look, because it's a long wavelength, doesn't bump into very much, makes it all the way into you. This can break your DNA bonds, and if it does, this is the primary cause of skin cancer, ultraviolet A. It causes skin cancer because it's lazy enough, it's got a long enough wavelength that it'll get into your tissues before it bumps into something. Let's go to the opposite extreme. UVC has a very short wavelength. It'll bump into something right away, guaranteed. It's so short that usually the first compound it sees, it'll give up its energy and break. So this is blocked by everything in the atmosphere. It breaks any bond, So it's all filtered or used up in the outer atmosphere. This doesn't reach us, which is good, because it would literally dissolve you. That might not be the right word, but it'll break almost any bond in your body. You just guys start to fizzle up. Yeah?
So what is sunscreen do? For UVA protection, so does that just have a chemical that is harder for the...
Precisely. What it does is it has chemicals that have bonds of a specific strength and distance where they are more likely to collide with the ultraviolet. So when you spread that on your skin, it'll use up the ultraviolet energy before the ultraviolet actually penetrates into your living tissues. Now UVB. UVB is exactly the right wavelength to match the shape of ozone, like this. So the reason we love ozone in the stratosphere up high is because that compound catches almost all the UVB and makes it into heat so it can't hit you. The little bit of UVB that makes it down, if it makes it all the way to the surface of the Earth, will almost always collide with skin cells on the outside of your skin, break chemical bonds on the surface, and not cause serious damage. By coincidence, a small amount of UVB goes deep enough to harm your DNA. But that's a relatively small percentage, because most of it is filtered by the atmosphere, and the rest has shallower impact. Stuff on the outer parts of your skin, not on the living cells underneath. Look, nothing really blocks this. So the majority of our exposure to the sun is dangerous no matter what happens. And everything will block this. So it doesn't even matter what's in the atmosphere. You don't have to worry about this stuff. What we are scared of is this one. Because it's primarily filtered by ozone. The wavelength matches the shape of ozone. And when we lose ozone in the stratosphere, the hole in the ozone layer, more ultraviolet B comes in. It'll usually run out on the outer parts of your body without doing serious damage. But if it makes it deep enough, it can break important bonds. So it raises the odds of skin cancer. Because you've got all your UVA exposure plus some extra UVB exposure. This is why the hole in the ozone layer increases cancer rates. First, second, third, fourth.
So all these wavelengths come from the sun, right?
Yes.
What's more dangerous, UVA or UVB?
Probably the A. Because the odds of it causing cancer if it strikes you are higher. It penetrates deeper. So it's more likely to reach a deeper layer where you have living skin cells. UVB is technically less dangerous because with a shorter wavelength, it'll usually do damage in the dead skin cells on the surface.
Is there like a legitimate hole in the ozone in
Yes.
that area, or is it like kind of thinned out all around?
No, it's a regional issue.
Where's the
It changes shape seasonally, it grows and shrinks, but it's a wobbling, oscillating shape, generally over the South Pole, and sometimes it peels off these little fins that stretch into Chile, Argentina, New Zealand, Australia. There's a smaller thinning of the ozone layer in the northern hemisphere. And by whole, we don't mean 0% ozone. we mean lower concentrations.
So it's not like they're like holes above every big city like New York and
No, the stratosphere is really active. It moves a lot, and ozone is formed naturally. So you have to accumulate stuff that taxes them first. Anybody else? Yeah.
How do plants and like their photosynthesis respond to different liquids?
The same way that we get cancer because of runaway growth, plants get damage to their DNA. Cancer technically does occur in plants, but their cellular growth is regulated differently, so they're more likely to just stop growing. They get symptoms very similar to what fire does. Yes?
And how does like tanning work? Is that like change bonds or why do you guys?
So tanning is an accumulation of a pigment that is added to your cells to block the sun. Your cells don't like the sun because the sun is dangerous. In response to sun, your cells go, dang, we're getting too much sunlight, and they start to paint the inside of the cells with keratin. Melanin. Melanin. So they add a pigment, I believe it's protein. Is melanin a protein? Ends with NIN. Does that make it a protein? Are you sure? No, I'm not sure either. They add a pigment which limits the amount of light that gets into the deeper living tissues. Generally, those pigments are in the dead layers on the outside. So you have a bunch of live cells covered by a bunch of dead cells, and the pigment is left behind when those outer ones dry out. Okay.
Does that make it take the rays, like the UVA?
They're more likely to absorb energy, so they'll usually soak up the ultraviolet before it reaches the living tissues beneath. Yeah.
So like going from being like pasty white to like getting a tan isn't bad in and of itself because you're getting a tan because of what your body's doing?
Your body is responding to damage. So going from pasty white to tan is
That means you've been
the injury.
Oh, because I thought it was like a response, like they started, so they paint things like this.
It is, but they do it after being damaged. Once you have a tan, you are technically a little less susceptible to skin cancer. So if you can very gradually build up a tan, that's going to lower your skin cancer exposure. The flip side is, if you're not usually dark, then you have to be exposed to the sunlight to get the tan, so you're increasing your exposure to limit your exposure. That's not smart. Essentially, we are very fragile beings.
Does this spray tan actually help or no?
What?
Does spray tan help or no? Like, does that do
Probably.
something or not even?
I don't know. I mean, sunblock definitely helps. I don't know if spray tan actually limits entry of ultraviolet. Something like that. All right. This is getting into minutia, so let's move on. Anybody know how much time we have left? 10 minutes. All right. Gabe, I'm glad you're entertained, but try to keep it down in the back. Salamando, please don't distract Gabe. He's got a lot of learning to do. There are 3 important details you got to know about the atmosphere. And remember, we've talked about many different parts of the atmosphere and many different problems in the atmosphere. So climate change was one issue. Man-made air pollution was another issue. Indoor air pollution was a fast one. Now we're talking about ozone. This is in the stratosphere. Yep. In the stratosphere. Number 1 fact you've got to remember. The atmosphere is big and complicated, but we've recently made it much more complicated. Humans have added a bunch of new chemicals to the atmosphere. Thousands of things that were never up there before. And in the outer atmosphere, there's already a lot of energy from ultraviolet, so chemistry is really tweaked up there. We've completely reinvented atmospheric chemistry in the upper layers. Fact number 2, anywhere you are in the atmosphere, there's oxygen. So whenever you do chemistry, you can just imagine oxygen is always available to react. Oxygen gas is one of the most common gases in the atmosphere. Finally, the number 3 thing you've got to remember is Hofbrinkel. Remember those diatomic elements that cannot be single? They need to be in a couple sometime. They are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. To demonstrate the formation of ozone, I'll need 4 volunteers in the front. Quickly, please, right now. Get up. 4. Come on. I need 4 volunteers. I need 2 more. Let's go, somebody. 1 more volunteer. Come on. Yes. Hold hands, please. Yeah, grab. Hold hands, please. Okay. Now, ultraviolet C, like we said, especially in the outer atmosphere, will break any bond. No. Will break any bond. So watch this. Aja! Okay. Now, if these were oxygens, they just cannot bear... They cannot bear to be alone, and usually they will reunite. Like that. But sometimes, when oxygen is split by ultraviolet, one of those will react someplace else, find a new place to live, and this desperate, clingy single will make ozone. Let's do this again. Oxygen, oxygen. Sometimes ultraviolet splits them. And if they're close enough to each other, they just reunite. Because of Hofbrinkel, they cannot be alone. And if they're close enough together, they'll find something, it's all good. But sometimes, one of them will be distracted into another interaction. So that desperate single needs to be part of some bond. And hearts will unite. And we get O3, ozone. Thank you, our volunteers. Thank you, volunteers. Thank you, volunteers. Thank you, volunteers. Thank you.
What's that
Iodine? Yeah.
But ozone's high enough that you're saying that this is at a lower level?
This is high because we had ultraviolet C to break it in the first place.
So this
I
is
think we should do that
good.
again tonight.
I guess so. Look.
Damn.
You shut up. Remember, the party got started when ultraviolet C split Jackie and Graham. We had ultraviolet C for this, so this only happens at the outer part of the stratosphere. Because ultraviolet C doesn't make it very far. Ultraviolet C is pretty much the only one that can break up oxygen. So please look up. oxygen split by UVC. Grav's not moving on very well. Grav, you gotta move on, bro. Put the phone down. Oxygen, UVC, 2 singles. Now sometimes these will just recombine, but sometimes one of the oxygens will combine with O2 to make O3, which is ozone. That's right, O3 equals ozone. Now remember, this happens in the outer atmosphere. Ozone is always being made. So now that these are illegal, the ozone hole will recover. Left to its own devices, the atmosphere will recover ozone because it's always being made. But please look up, it's also always being broken because there's ultraviolet B that can split. So you get what's called natural decay of ozone. O3 doesn't last forever. Sometimes those singles split off from ozone.
But then they find something else.
Right. So this is a dynamic equilibrium where ozone is being made on one hand and being broken up on the other. Both of these are natural. Tomorrow, we will break up even more ozone by adding ingredients to the atmosphere that peel apart ozone, but don't last very long. Yeah.
Can only UV bring apart the ozone, or can
UVC can do this too. It just usually is in the outer parts of the atmosphere, and technically UV ozone, once it makes a 3, tends to start weighing down. But yeah,
What's off of hydrogen?
hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine.
So what's the relevance of that again?
Those are clingy singles. They cannot live on their own. If you ever see a single one in the atmosphere, it'll be in a bond within about 100th or 1,000th of a second. Yeah, I remember that. Those are very briefly atomic oxygens. Yes. I would have called those this, an O with an asterisk. They can't be alone for very long at all.
What should we do with the Petri dish?
Students, you will dispose of your Petri dishes and bring your loops back to me now. Bring your loops back to me. Bring me your loops. Trash your Petri dishes, bring me your loops. Trash your Petri dishes, bring me your loops.
Oh, I forgot to get it downstairs.
Trash your Petri dishes, bring me your loops.
That's genius.
Wait, Valentine's Day. Hashtag prom next year, please.